So that was written a couple months ago. I work for Continuum Analytics now, so this is why I'm working on Dask. So that was back in grad school. So this is the Dask talk, Dask out of core NumPy and Pandas through task scheduling. So we're going to cover a couple different things today, but we're going to start with a motivating example. So I have some ocean temperature data living in netCDF files on my computer. It's the daily mean ocean temperature every quarter degree around the globe. So a 720 by a 1440 array every day. It's taken from that address there. You can get it for yourself if you want. So handling 1 year's worth of data works really slick in Python. Pull it up in netCDF4, open the data set, do some NumPy operations, and then make a nice fancy plot in Matplotlib. And that worked out nice. It's only a couple lines of code. Everything kind of talks to each other smoothly. But what do you do if you have more data? So here is 36 years worth. This is about 15 gigabytes on disk. If you uncompress it, it's about 51 gigabytes. That is not going to fit in the memory on my laptop. So I can't just load it all into NumPy. What do I do? So one possible solution is to use blocked algorithms. So a blocked algorithm is basically taking your problem and breaking it up into much, much smaller steps. So here's a blocked algorithm for mean. So say we have some very large on-disk array stored as an HDF5 file. It's a trillion elements long. We could break it up into 1 million element chunks. We could take the sum of each chunk and save it, toss it off somewhere. We could count how many elements are in each chunk and save that somewhere else. And then at the very, very end, we do kind of an aggregate to pull all the results back together. So we take the sum of the sums and we divide it by the sum of the counts. And so this has allowed you to iterate through, never having all of that array in memory at once, but still be able to handle a larger data set. So if you think about this problem more, if you look at it, each of those chunk operations doesn't depend on any of the other chunk operations. So this kind of for loop that Python would run through, it would do chunk 1, chunk 2, chunk 3, chunk 4, doesn't actually need to be done sequentially. You can kind of break it out into a parallel operation. And so if you were to write that down as like a directed graph, it would look something like this. So we're taking the array, we're breaking it into many, many, many chunks. We are performing a mean kind of a operation on each chunk, getting the sum and the count. And then we have some kind of reduction. So it's kind of a map over all chunks and then a reduction over all of it. So blocked algorithms allow you to handle these data sets in parallel and use a lot lower RAM. But the complicated part is figuring out how you can chunk it. How can you actually make what your computation you want to do into kind of a blocked algorithm? And so this is where Dask comes in. So Dask is a parallel computing framework that leverages the excellent existing Python ecosystem. So all of NumPy, all of SciPy, all of that, we don't really want to mess with it. It's good, it's tested, let's leave it alone. We use blocked algorithms and task scheduling to actually do these computations. And it's written in pure Python. So it's pip installable, conda installable. You can get it pretty easily, not anything to compile. So Dask, here's the underlying architecture. On the bottom, we have a graph specification. So if you saw that graph we had before, doing the blocked mean, that little directed acyclic graph, that's how we describe those computations in memory. And then on top of that, we built some schedulers to actually execute the graphs. And so these two blocks, the red ones there, we would call like the Dask core. This builds up the base of Dask. And then on top of that, and the rest of the Python ecosystem, we have built a couple collections. So leveraging the already existing Python libraries, but kind of adding in the blocked parts that Dask gives you to actually perform computations. So we have Dask Array, which is kind of like a out-of-core ND array library. Dask Bag, which is an unordered collection. It's good for working with JSON blobs and other things. And then Dask Data Frame, which is kind of like a Pandas data frame. So we'll start with Dask Array. So Dask Array is an out-of-core, so you don't need to have everything in RAM at the same time. It works off disk. Parallel, so it can do some computations in parallel, and we'll be talking about that a little bit more later. N-dimensional array library, so similar to NumPy. Copies the NumPy interface, so you can do broadcasting arithmetic. You can add two arrays together and it'll work. Reductions like mean and max, slicing, fancy indexing. We have some linear algebra operations. Not all of those can be done blocked, but we have some. TensorDot, QR, SVD. We recently got SVD compressed, which is kind of cool. And then we also have some new operations, so some parallel algorithms that aren't in NumPy, approximate quantiles, top K. We have some functionality for slightly overlapping arrays. So if you're working on windowing operations, say image analysis, like what scikit-image would do, you can have computations that talk to other blocks but just slight edges. And then we work well with HDF5. So here is the fun part of the talk. Let's see. So I'm going to open up an IPython terminal. Ooh. And import dask.array as DA. And import numpy as NP. Can you all see that? Is that, it's a little small? Okay, make it a little bigger. Is that better? A little bigger still? Okay. So first I'm going to create a NumPy array just for the demo. So we'll make it a 100 by 100 array. And then we'll read that all into Dask. So DA, Dask array from array is going to pull in anything. It works with anything that uses NumPy indexing. So this can work with NumPy arrays. You can also work with HDF5 files on disk, really anything that you can kind of slice into that way. So for the demo, just a NumPy array. And the only other thing you need to pass in is chunks. So this is what the block size is going to be. So it's a 100 by 100 array. So we're going to break it into 50 by 50 blocks. And that's it. And so no computation's been done yet. It's just set up how we can actually get the data into the system. So that's what it looks like. If I do a little tab there, you can see all the operations it supports. Looks a little like what a NumPy array would look like. You can do, a mean or whatever. And so that's not actually doing anything. That's building up the computation. And so this is where the cool part comes in. You can actually visualize those. Oh, am I not? Hang on, environment issues. Okay. And so that's what the mean operation looks like. And so you can keep building on those. So we could go we could do a dot with its transpose. And so that would get a little more complicated. We could then take the mean of that if we wanted. Could take the mean along an axis. Maybe sum that afterwards. And then, I don't know, add 10. So you're describing your computation, but it's not actually doing anything. This is just building up the operations you would like to do. And then at the end, when you actually want to compute something, you make a call to compute. And so this starts walking through that whole graph using threads or processes or what have you to actually perform the computation. And we have some pre-optimization steps that are built into each of the collections. So it might condense some of these tasks. And here we'll actually call compute and get it. And so if we visualize what that looks like, let's open that back up. So the task schedulers actually perform the computation here. And so here we're walking through a graph for a very parallel operation. This could be some kind of reduction along an axis. And so blue is computed. So circles are tasks, squares are where data lives. Blue is computed for circles, task is completed. Blue for a square means the data is released. So blue is good, blue is done. Red means it's not released yet for data. So the square boxes, we've saved it in memory still. It needs to be used for another task afterwards, or the task is still running. So we want everything to eventually be blue. And so this works pretty well. We try to push through computations, try to limit how much stuff is in memory at a time. Sometimes it breaks down. So at some point in here, that entire middle row is going to become red. We didn't actually have a sufficient algorithm to push all the way through. So those two big circles should have been computed first because they're the limiting factor. So we've been doing some work on improving the scheduler, but right now for most problems it's usable. This actually isn't a bad fail case. We have mechanisms for spilling to disk. So even if these were very, very large arrays, this wouldn't kill your computer. They would write to disk. It would just be slightly less efficient than it could be. So we're always trying to improve. So going back to our original Ocean data set, we can actually do that computation on those 36 years of data just using Dask. So it's just a couple more lines. We create a data set for each file. So that's what that list comprehension there, the data set netcdf. That's still not loading anything to memory. That's just kind of pointing to the file. And then after that, we concatenate them together using da.concatenate, similar to NumPy concatenate. Do a mean on the axis. X.mean axis 0 looks just like NumPy. And then we pass that into matplotlib to actually make a pretty plot. So you don't always need to call compute. Dask arrays support the array protocol, so anything that expects a NumPy array and will implicitly convert will just actually do it. So this passes into matplotlib, and we get a nice plot out. So this is the average ocean temperature since 1981, averaged over each individual spot. So that was all done on my laptop. Took a couple minutes, but I was able to work on 50 plus gigabytes of memory on a laptop, which is kind of cool. So we also have data frames. These, in their latest release, Dask 0.6, have become usable. So this is actually something you can use if you would like to do work. It's still missing some functionality. We only implement a small part of the pandas interface so far. Some of that is because we can't do it efficiently. Some things can't be easily blocked, and others just haven't been accomplished yet. The best way to get an operation that you want to use is to bug us on the issue tracker. So some things we do have. Element-wise operations, you can add to series. I'm not going to go through all of these. Value counts, we do group by aggregates pretty well. Joins on indices. Some things we can also do that aren't quite as efficient. They have to shuffle through disk a little bit. So group by applies, joining not on an index. But these are just a few of the things we currently support. So a little problem set. The yearly CSVs of all American flights since 1990. So this contains information on times, so departure times, arrival times, what airline it was, where they flew from and to. Can be gotten from that URL there. So for that, we can use Dask data frame. So the first thing we do is create it in from reading a CSV. We do a little glob on files, so star.csv. We're only reading in a couple columns. The origin, so where did the flight take off from, what time it took off, what time it was supposed to take off, and if it was canceled or not. We then break them down into time series. So if it wasn't canceled, so we don't want to worry about the canceled flights. And then if those were delayed, and then we count flights per airport, total flights per airport, and then delayed flights per airport, figure out what % of each airport was delayed over the last 20 years. And then we strip out the airports that have less than 500 flights a year. So those little airports in Alaska that get 1 or 2. And so that's about 10,000 for the entire data set. And so at this point, no computation's been done. We've just created one of those graphs. And so to actually do it, call compute, and that pulls it into a pandas data frame. So we started with 10 gigabytes of data on disk and kind of pulled it down into one number for each airport, which is a very manageable thing, and pandas can handle very well on my computer. And so then after that, we can do a little finishing up computation, so sorting it and then printing out the top 10 airports that had the most highest % delay. So Atlanta was the biggest culprit there over the last 20 years for delayed flights. So looking at the memory profile for that, it was 10 gigabytes on disk. We had to read about 4 gigabytes of that into memory to actually perform the computation. The max memory during that was only 0.75 gigabytes. So our schedulers performed very well, only loading in what memory was needed and then releasing it after doing it. So the chunked algorithms worked very well for that. So we've talked about the collections on the left there. So those build task graphs. On the right, we have the schedulers that perform the task graphs. The unifying thing is what a graph actually is. So a Dask graph is a dictionary of name. So a name is any hashable, like for any dictionary. And then a task. So a task is a tuple of a function and then all of its arguments. Kind of looks like Lisp if you're ever written Lisp. And then args can be names, values, or further tasks. So you can have nested tasks. So on the left here, we have some Python code. taking A and B, incrementing them, and then multiplying them together. And on the right, we have a Dask version of that. So they look fairly similar. It's mildly readable. So Dask collections fit many problems, but they don't fit everything. So you can create Dasks directly if you need a custom pipeline. So we have a load step, loading some memory or data from files, cleaning it, doing an analyze, so kind of aggregating those together, and then storing it. So you can create a Dask directly yourself for things that don't fit in kind of Dask array, Dask bag, Dask data frame. Final takeaways. Python can still handle large data using blocked algorithms. You don't need to move on to something like Spark or Hadoop necessarily. Dask collections form task graphs expressing these algorithms. The schedulers execute the algorithms in parallel, trying to limit memory. And the graphs can be directly created for custom pipelines. So if our collections don't work necessarily for your problems, you can drop right into working on Dasks directly. Any questions?